order derivatives. Sounds scary. I gave you a little tip a little bit earlier. I told you if you've been keeping up with things, this is the easiest lesson maybe of all of them. I would say trust me, but you don't know me that well. So you're going to find higher order derivatives, and we've got one simple example where you go from a position function to velocity and acceleration functions. Position just means from a certain place, how far away are you? Easy as that. Velocity, how fast are you going away? Acceleration, how fast are you increasing your velocity? That's the whole idea. Second, third, and other higher order derivatives. Like I say, trust me, this is easy. So this is what the standard derivative looks like. F prime, y prime, dy dx, all of those represent the first derivative. Now if you take that first derivative and take the derivative of that derivative, we call it the second order derivative for obvious reasons. Second on the list. Start with the function, first derivative, second, third, and fourth. You can go as far as you like, really. Although usually at some point you run out of anything to take the derivative of. If you're talking about starting with a regular polynomial, eventually all the rest of the derivatives are zeros because you work your way down to where it's a constant, and the derivative of every constant is zero. So you're sort of at a dead end unless you're really obsessive or whatever. We won't go there. So here's an example. These are just notations, so you can take a look at what we've got here. First derivative, those are the ones we've been working with so far. And just so I'm ready when I want to make some kind of a mark, I'm going to sneak down here to lower left, and I'm going to change to a pen as opposed to a highlighter or whatever, because I can always use something else as a highlighter. Next. Here's a real simple one. This is a good starter one. So even after I've worked this one out, you can go back later for yourself, go to this slide, and see if you can do it without checking the recording. So it says find g prime 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 of 2 with function g of t equals, and there's your function. So first of all, you have to find out what g prime 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 is, or g triple prime, or whatever you want to call it. So where's my marker here? There we go. So here's my g of t. So the first thing we're going to do is get the first prime. Bring that 4 out front, negative 4t cubed. Bring this 3 out front, 6t squared, plus bring this unspoken 1 out front, and there's our derivative. Of course, this gives you 0. We're looking for triple prime or triple derivative, so let's go to the next step. We've already got g prime of t. All we have to do is take what we've got here and take the derivative of that. Bring the 3 out front, negative 12t, you're down to a square. Bring the 2 out front, 12t to the first, we'll leave out the 1, and 0 at the end. Notice that as we're going, we're losing one term. If we've got all the terms, we don't have quite all of them. 4, 3, the second one wasn't there, t and constant. We're dropping 1 each time. So we've got g double prime. Now we're ready to get g triple prime. So bring that 2 out front, negative 24t. Bring the 1 out front. 12. There's t third derivative, and that's of g of t. It's that easy. Now it says find g triple prime derivative-wise of 2. All you need to do is put the 2 in where the t is here. So g triple prime of 2 equals negative 24, take off t, put in a 2 of course, and 12 is just 12. And what do we have? Negative 48 plus 12, and we know that's a negative 36. Hopefully you did not jump to your calculator. Don't feel too bad, but see if you can do some of these things by yourself. Your calculator is an assistant, it's not your main driver. First derivative, second derivative, third derivative, they're all there, and put the 2 in. And there you go. It's the value of the third derivative when t equals 2. And we're almost 1/3 of the way through the lesson already, and it's pretty easy, right? As I just mentioned, notice, where am I? Where's my marker? There. Note, every time you take a derivative, the degree drops by 1. Because every time you take t to the 17th and take the derivative of that, the 17 comes out front, and you're dropping the degree by 1. That's what it means. And if you do that long enough, eventually your derivative becomes a constant. Eventually. There's a little bit of a picture, and this is a little bit of a hint. Notice that in the example they show right here, they're showing all the powers of n. All integer powers of n, by the way, which makes it a polynomial. If you keep doing that, and this n represents which derivative do you have here? So you've actually taken the derivative n times. Now if this first number right here is a 1, then what you'll see out front from the leading term is a coefficient of n factorial. 1 times 2 times 3 times 4 and so on, like this. It's just a regular times sign, it's not x. If I'd wanted x, we've got something that looks a little bit more like that. Above that, all you have are 0 functions. Find the first 4 derivatives of this one. Now this one, notice, first of all, it's not a polynomial. Polynomials have exponents that have positive integral degrees, like 1, 2, 3, 4, 5, 1,562, for example. This one's a little bit different. Notice also that whoever made this example decided, ooh, this is Mr. Saylor's group. We're going to be nice to them. We're going to rewrite it before they actually get it. So here's our rewritten function, and we'll start taking the derivatives. First derivative. Bring that negative 1 out front. Don't need the 1 sticking there. Remember, we're subtracting 1, so it becomes -2. Next one, bring the -2 out front. We'll go to +2, subtract 1. Actually, the exponents are getting bigger, but further to the left on the number line. Third derivative, and that's usually as far as we take those apostrophes. Bring the -3 out front, -6, x, -4. Notice that because we're starting with a negative number here and as the initial exponent, each of these coefficients flips in sign, positive to negative, positive to negative. On this next one, the other thing to notice that is once we get past 3, the typical way of doing that is because it becomes a little bit annoying to have all of these marks out here. If I wrote something like this, for example, you'd be a little bit annoyed at me because then you have to go in there, and if it's on the screen, it's really bad because you have a hard time adding up or numbering which ones those are. 1, 2, 3, 4. And if you're not careful, you can lose track inside. Whereas if you use this version of that notation, you know exactly which derivative it is. So going from the third derivative to the fourth derivative, bring that -4 out front, you're up to 24, and you're down to a -5 for the exponent. Guess I got a little bit sloppy. That's how you do it. It's that easy, really. Of course, we can rewrite each one of those. Notice that the coefficient out front, first you have a 1, then a 1 times 2, 1 times 2 times 3, 1 times 2 times 3 times 4, and so on. Okay, acceleration. So you've seen the velocity is the derivative of the position function. Now in physics, for example, you might see this position function looking something like this. Now you won't see this on most of the slides. This is my version of it. So this S represents division, or position. Now, here's my take on it. Not too bad, I don't think. And I've probably stolen this from someone, but first of all, if no time has gone by at all, then where you were to begin with is where you are now. This 0 represents, if you looked at your stopwatch or you looked at your clock, 0 time has gone by. And sometimes you might see an F there for final distance. This would be how far it is from some place at time 0, or another way you might put this is I for initial distance from some arbitrary position. And this represents what's the final position after a certain amount of time has gone by. Now, if it's been going a certain distance and it's got some initial speed, here's initial speed, multiply that times how long it's been moving at that speed, and you can find out how far it is from that certain starting point. Not starting point, but initial point that you're comparing all these distances from. So, for example, on the interstate, if you went out right now to the interstate, Maybe you're at mile marker 72. Mile marker 72 on Interstate 85. Now you just started, so what's the 72? Well, 72 refers to where I-85 actually started counting miles. Somewhere near the Georgia border, if I'm not mistaken. And when you get up to the North Carolina border, it says about 106, which means 106 miles from the Georgia border. And then once you get into North Carolina, what you see next is mile marker number 1, because you're talking about how far you've gone on Interstate 85 from mile marker 0, the border. So this represents where you're starting from, like our mile marker 72 out here on I-85. This final distance represents how far you are, where you are, when you actually come to a stop where you finish your journey after a certain amount of time. In a similar fashion, its velocity can be found by taking the derivative of the position function. Now this would assume that you got on I-85 and you stayed the same speed the entire time. We know that isn't what usually happens. Usually we speed up or slow down depending on traffic. And when we do, there's a rate of change of the velocity. That's also known as acceleration. And if you're slowing down, it's called acceleration. It's usually referred to as deceleration. De-acceleration or slowing down. Here's the position function. There's the velocity function, first derivative of the position function. There's the acceleration function, which is the derivative of the velocity function, which is the second derivative of the position function. Position, velocity, acceleration, each one is a move up on the derivative continuum. So here we've got an example, and take a look at that for a second while I get a drink. If you look at the picture that's given on the right, notice at the bottom it says not drawn the scale. And you might think, well, how do I know it's not drawn the scale? Well, even if this is a 6-foot person here, 160 feet would mean a lot more people could be stacked up here to get us to that person's position. Now what someone has done is put these things together. This person with some long hair, so sometimes you might think that's a girl, but not necessarily. This person's at the top of a 160-foot cliff. You might also, if you've been out west, you might recognize that usually along the coast, the west coast, cliffs are more likely to look like this. On the east coast, the shoreline usually looks a little bit more like that. Anyway, the initial velocity of the ball is 48 feet per second. So notice the person has thrown the ball upward. So initially it's going in the air, and what we have is it's going 48 feet per second, pretty fast. And the position function looks like this. Now what does that S represent? Well, at some point Let's say there's a point right here. The ball gets to that point. That's where it is after t seconds. And the way we can find out what that is take the 160, because that's where it started. Because the person threw it upward, it's a positive 48. So 1 second later, throwing it upward makes it go up in the air, which adds to the 160 feet that it is above the water. But at the same time that's going on, gravity is working too. Gravity tends to pull it downward. And this negative just means that it's a downward inclination. So it says find the height, velocity, and acceleration of the ball at t equals 3. Well, we can do the first part pretty easily because here's our height function right here. If we want the height at 3 seconds, all we need to do is put 3 seconds in for all those t's. You can use your calculator easily to find that. In fact, you probably wouldn't have to use the calculator. That'd be good practice. Well, what about velocity? How fast is it going 3 seconds later? Well, the velocity is the first derivative of the position function. So the first thing you'd want to do is find out what the velocity function is. Since this is the position function, we'll take the derivative of that with respect to time, and that'll give us our velocity function. So bring that 2 out front. That'll give us a negative 32. 2 minus 1 gives us just a straight t. Take the derivative of 48t. That gives us just 48. And the derivative of 160, of course, is 0. There's our velocity function. Now if we want to find the velocity at 3 seconds, the velocity equals the derivative of the position function. And all we need to do is put the 3 in for t. And if we look back here, we'll just bring this in. We have negative 32. We're interested in the 3 second mark. There's our 48 constant, and we can easily get that value. Next, we also want the acceleration. The acceleration is the derivative of the velocity. Acceleration is the derivative of the velocity with respect to time, which is the second derivative of the position function. So all we need to do is take the derivative of this part right here. The derivative of the first part is just a negative 32, and the derivative of 48 is 0. There's your acceleration. To be more precise, it's 32 feet per second squared. And those of you who may have taken physics in high school, you might recognize that as g, the acceleration due to gravity at sea level. This value is actually different at different places. Most of us are close enough to the sea level that this g of negative 32 is always what we have. If we were several thousand feet in the air, this would be a little bit different, a little bit less, because this refers to the acceleration due to gravity at sea level, or at a certain distance from the center of the Earth, or the center of the mass of the Earth. Enough physics. So there's our position function, our velocity function, our acceleration function without the units. Remember the first one? The units, where's my marker? There we go. The units on this one will be feet. The units on this one will be feet per second, just like miles per hour. And the third one is feet per second squared. Keep that in mind in case you have to answer a question about position, velocity, or acceleration. You need units that look like this. It could be miles, miles per second second squared, miles per hour squared. There are lots of possibilities. So to get those, all you have to do is put the 3 in for the time. There's your velocity, and there's your acceleration. Acceleration due to gravity in this case. Notice that that value of 32, or the negative 16, whichever one you're looking at, would be different if you were living on the moon instead. Somewhere around 1/6 of what it would be here on Earth. Notice I highlighted this one over here. Where's my marker? There we go. The negative value means it's being pulled down toward the Earth. Now it has one with the moon. That's a good one. Here's a position function for the moon. We could do the same thing for that. You can use a position function for any kind of objects at all. Whether it's a ball, whether it's a hammer, a feather, it doesn't make any difference. Here's another one. It's a little bit different. The velocity for a certain automobile starting from rest. A little bit more challenging in this case, because this one has a fraction. So if you wanted the acceleration of this one, thinking ahead, what you'd have to do would be rewrite this, perhaps, or just use the quotient rule to get the acceleration function. It's the velocity function, and maybe you'd want the acceleration function. So there's the quotient rule, and there's the acceleration function. You can look at a table with those, and you can see what's happening. These are the times up on top. Where am I? There we go. These are the times in intervals of 10 seconds. So for the velocity, all we'd have to do is go back to the velocity function, put the 0 in, the 10 in, the 20 in, the 30 in, and so on. I showed you a couple tricks for that one. There's a couple different ways of doing it. The one I showed you is use the function you're given, and if you put that in your calculator, you can make things work pretty quickly. Or you can do it the long way. Type in that same function over and over again using different values of t. It's up to you. If you take, for example, now notice down here, where am I? There we go. This is the acceleration, the derivative of the velocity function. And this takes it at 10-second intervals, which means if you take the velocity and the time for the first 10 seconds, you can get the acceleration. If you take it for the next 10-second interval, you can get the acceleration by using the slope formula. It's that simple, really. So next time you're in a car, you're taking off, notice that what you feel actually is the acceleration of the automobile. While you're actually going at 50 miles an hour and the speed isn't changing, you don't feel a thing. It's almost as though you're not moving, although look out the window and you can see you're moving. It's the acceleration that gives you the feeling of movement. Try your exercises, see how well it goes. Until next time, I'll see you.